Hello, uh, am I audible? And can you guys see my screen? I'll just go ahead and wait for 5 minutes and let more people join before we begin the session. Okay, we'll start at around 9:45. Let's just let a few other people join before we begin. Yeah, okay. You guys can hear me, right? Am I audible? Uh, okay, so it's 9:45 now, so I'll go ahead and begin with the session. So first off, hi guys, my name is Taran, and I'm a senior co-member of CodeChef-VIT. So in today's event, I'm going to be demystifying machine learning, like from the algorithms to what all marvels it can accomplish, like I'm pretty sure everyone has used it by now, but ChatGPT, etc. All those wonders stem from very simple concepts that may initially seem very complicated, but are actually quite easy. So let's go into it. So the agenda of today's session is, well, first I'm going to go over the basics of machine learning, like what machine learning is, then deep learning versus machine learning. Then I'll be covering one of the neural networks, artificial neural networks, and then how it's visualized. There's a TensorFlow website that allows you to visualize ANN, and I will show you a practical implementation of it. Okay, so let me go over the basics of machine learning. So first off, what is machine learning? So that's quite simple. So any technology where models are trained on historic data in order to perform certain tasks. Say, for example, let's say a bank, based on your CIBIL score and other contributing factors, they decide whether to give you a loan or not. Or let's say face detection in CCTV cameras. All those are various applications of ML. So ML is divided into majorly two categories. So the first one is supervised learning, and the next one is unsupervised learning. So supervised learning, in very simple terms to explain it, it's where we have historical data and we have a particular output. Say the loan prediction, the loan decision whether to give it or not, we discussed earlier. So we have data based on the customer attributes and whether or not to give them the loan. So since we know the output, which is to whether to give the loan or not, it comes under supervised learning. And for unsupervised learning, let's say we have let's say we have a bunch of images of vehicles, planes, cars, motorcycles. So we can use the nearest neighbors algorithms for clustering. Basically, we can use hierarchical clustering in order to segment those images into the various different categories. Obviously, now there are way more sophisticated techniques, but earlier this was what was used. So some examples of supervised learning are regression and classification problems that can be solved by a tree, by SVM. And for unsupervised learning, you have various clustering algorithms. You have KNN, then you have, like I said, hierarchical clustering. So yeah, so so far that's the basics of machine learning. So let me contrast deep learning and machine learning. So as you can see from the diagram given here, deep learning is actually a subset of machine learning. Now, you guys might be wondering what the graph on the left-hand side of the screen is. So the x-axis here is the amount of data, whereas the y-axis is the performance. So the issue with ML is, as the data scales, as in we get more data, it plateaus. I'm talking about the traditional ML algorithms, but DL scales with increase in data. So that's why whenever we have like large data, like let's say if I'm working with a flat file of 100,000 rows, you can classify that as a big file. So you would use deep learning algorithms ideally because they would do certainly way better than traditional ML algorithms. And what better way to get into deep learning than to talk about neural networks? So I'm going to teach you guys about artificial neural networks today. So as you can see on the left, there's the architecture of artificial neural networks. So these nodes, the three nodes here, are neurons. They're called neurons. So these three neurons are known as the input layer. The middle layer is known as the hidden layer, whereas the last layer is the output layer. So I'll explain how exactly the ANN works. So before we move on to more complicated architectures, let's understand the basic component of a neural network, which is basically a neuron. Okay, so honestly, the only prerequisite you need to know to get into, well, ANN is linear regression. So if you know y is equal to mx plus c, you pretty much already gotten it. You pretty much got a very core fundamental concept of ANN. So, okay, let's consider this neuron. And we have inputs x1, x2. So x1, x2, up to xn are the attributes of the data. So say, for example, you're working with an Excel sheet with, say, 26 columns. So your inputs are those 26 columns. So it'll be from x1 all the way to x26. Now, each input goes into the neuron with a certain weight. So this and it has a certain bias. I'll come to the bias term later, and as well as the activation function, I'll explain more about it once we see the visualization. So basically, what the neuron does is it's taking a weighted average. So let's ignore the activation function and bias for now. So say you have an input x1, then you have an associated weight with you w1. So these weights are randomly generated initially. You can do something known as transfer learning, where you get weights from a other model to use in your particular data. But say we're building one from scratch, so the weights are going to be randomized. So let's take x1, and it has a certain weight associated with it, w1, and then x2 has w2 associated with it, and so on and so forth. So what this neuron does is it takes a summation of all of this. So what I mean by summation is it'll take the sum of the product of x1 and w1. So if the output, the y predicted of this neuron would be x1 into w1 plus x2 into w2, so on and so forth till xn plus wn. And your output will also be a linear function. So your output y is basically x1 w1 plus x2 w2, so on and so forth till xn wn plus the bias. And to explain this concept better, TensorFlow does have a visualization tool. So let me go into the visualization tool so you guys have a better understanding. Okay, so yeah, so this is the website. So epoch, I'll explain what epochs, learning rate, activation, I'll explain all of that a bit later. So for now, let's mainly focus on these. So this is the data. So this is a classification problem. And we have our features. Our features are basically the attributes, the inputs, x1 and x2. So if you look at this, x1 is a function that's basically just the y-axis, and x2 is the x-axis. So from these inputs, we have hidden layers. Here we have two hidden layers. This is hidden layer 1 with 4 neurons, and hidden layer 2 with 2 neurons. So as I said earlier, this neuron has a weighted summation w1 x1 plus w2 x2. Similarly, this neuron also has a weight associated with x1 and x2. Here the weights can be different. We cannot say until we look at the weights. Here we can see the weights between each are clearly different. So the beauty of deep learning, or neural networks rather, is it creates features from already existing features. So what I mean by that is it basically extracts new features that were previously not there. So this is one of the advantages of deep learning. So let's say x1 here, it's extracted a particular feature and it has given us this particular output. The white line is the output of this particular neuron. So it's extracted a particular feature. So now let us take this data set first. Okay, so let's go ahead and run this. So as we can see, based on inputs x1 and x2 and the two hidden layers of 4 neurons and 2 neurons each, it's able to construct a boundary which can easily classify between the orange and blue dots. Now let's move on to let's take this particular data set and let's go ahead and run it. So as we can see here, if we look at the metrics here, the test loss and training loss. So the loss is basically, so how I explain loss is how far your model has predicted from the actual value. So you want to decrease your loss as much as possible. But if we see here, we cannot make any clear-cut boundaries. Even if we increase the number of neurons, we still will not have a distinct boundary. So the reason for this particular phenomenon is we're making features of a linear model. So in the end, since it's a weighted summation of linear inputs, your output will still be linear. So to tackle this particular issue, we have to introduce non-linearity, as in we need to make the boundary line not straight, in simple terms. So that can be done in one of two ways. So one way we can possibly do it is, as we can see, let me just decrease the neurons. So as we can see here, we have x1 squared and x2 squared. So that's a way of introducing non-linearity. So let's go ahead and take x1 and x2 squared. So the equation of a circle is x1 squared minus g plus, is x minus g the whole squared plus y minus h the whole squared is equal to r squared. Basically, it has non-linearity in it. It has a polynomial term, which is x squared. So we can take x squared, x1 squared, x2 squared, and x1, 2. And if we run it, yeah, there we go. We get the boundary line. So one way to introduce non-linearity is we manually introduce it by modifying the features. This can be done in feature engineering. Or here's the important term. Like here we had discussed the activation function. So I will show you the main reason you have an activation function. So the activation function is to create that particular non-linearity. So let me go ahead with x1, x2. Okay. And let's go for, okay, so these activation functions basically restrict your output to a particular range. So let's take tanh, for example. So what tanh does is it restricts the output of the neuron. So let's say the neuron gave an output of 20. So what tanh does is it restricts it to a value between +1 to -1. It can be any value from +1 to -1. That's the tanh activation. So let's use the tanh activation to see whether it can form a good decision boundary. Yeah, there we go. So as we can see, it's the non-linearity is introduced and we can clearly make a decision boundary. So this is the importance of a activation function. So there are various different types of activation function. So let's take ReLU, for example. So what ReLU does is it basically converts any negative number of the neuron. Let's say the output of the neuron was -20. It would make it 0. And if it was +23, it'll remain +23. Basically, the ReLU function is the mod x function. It cuts off all negative values and makes it 0, and any positive values remains the same. Let's try running it with ReLU. So ReLU has created this decision boundary. So what happens if we add more? Let's add more neurons and let's see what happens. Okay. So if you guys have noticed this, the more neurons we've added, the less sharp edges there are. That is the function becomes more differentiable the more neurons you have. But adding more neurons has its own drawbacks. So the main drawback of adding like lots of neurons is overfitting. So you have to be careful. So deep learning is a lot about experimenting. You just have to experiment with the layers and see what works best. So that comes under optimization techniques. So I'll explain optimization as well. Then also, yeah, let me explain sigmoid, which is another important activation. So what sigmoid does is it's basically used for classification. It restricts your neuron output to 0 and 1. And yeah, linear activation function is what we were using before. It's basically, it just lets any output through the neuron. Okay. So let's move on to a more practical example. So I've created a notebook. So in this notebook, it's basically predicting the churning rate of a customer. So the data set has been taken from GitHub. And if you see the data, this is the data we have. There are, I have added, yep, there are total of 46 columns, and there are no missing values here. And these are the data types. So gender is int 64 because it's 0 and 1. So this file that I've taken is a flat file. So what I mean by flat file is the data has already been pre-processed and clean. So ideally, so this is an ideal circumstance where you have like very good data. But in reality, you're not going to get such data. So it's important that you clean the data. That there are various methods of cleaning it, and it's quite simple to clean the data. So let's go ahead. Let's go further ahead. Okay, so we're going to here where I'm importing a normalization factor. Here we're using the min-max scaler. And so what the min-max scaler basically does is it's a way of normalizing the data. So suppose you have, let's say, you're trying to predict a certain output, and your input variable, let's say there are two input variables, your age and your income. So if your age is obviously going to be between maximum 20 to, this is for people who are about 20. I'm just going to assume they're about 20. So the age will mainly range from 20 to 100, and the income, however, will be, it's a huge range. It can be from 0 all the way to like crores of rupees. So the issue with this is, since the scales aren't the same, your model will be skewed towards the higher value. So since the range of your income is very high, your model is going to be more biased towards income and not factor age at all. I mean, there will be slight factorize. It'll obviously take into consideration age, but it'll not play as important of a role if you don't normalize the values. So what I mean by normalizing the values is to bring it down to a, a certain scale, like restricting, like how the activation function restricts to a certain range. So by normalizing, you're also restricting it to a certain range. So this helps avoid bias. And it's important to note that when you're creating your train test split, it is important you split the data first before you normalize it. So what I mean by that is, you create your splits, and then you perform whatever scalar you want to use. So you might be wondering why you do this. So the reason you do it is, if you have only a limited amount of data, and you're using that entire data set to create your normalization. Let's take uh okay, let's use min-max scaler itself. So what min-max scaler does is, it takes your data point. Let's say you have 10, 20, 30. So it takes your data 10 and it subtracts it from the lowest value and then divides it by the range. So if you take 10, 20, 30, the lowest value is 10. So 10 minus 10 is 0. So let's leave that. Then you have 20. So 20 minus the lowest value 10, which is 10, and you divide it by the range. The range is the highest value minus the lowest. So that's 30 minus 10, which is 20. So you get 10 by 20, which is 0.5. So that's how the min-max scaler works. There are various different ways of standardizing the data. So I would suggest you go ahead and look, and depending on the data, the type of scalar you would use is also different. So in this case, I've gone ahead and taken min-max scalar. You can go ahead and take whatever type of normalization method you want to go for. Okay, right. So getting back to the main point. So why do we split the data first and then normalize it? So we do that to prevent overfitting, in a sense. Because if your scalar takes into consideration the testing data as well, there will be bias, because of the testing data, the range can increase. If you're normalizing it via, uh, let's say, normal distribution, then adding the test values will obviously change the standard deviation as well as the mean. So this is why you you split the data first and then you normalize it to prevent, well, bias, to prevent overfitting, so that you don't get overly positive values. So I have imported the necessary packet. So here, what we're predicting on is the churn rate. So by churn, whether the customer will remain. This is a telecommunication service. This data says telecommunication service. So based on these 45 attributes, we're predicting whether a customer will, will remain a customer or they'll switch over. So that's basically churn. So we're predicting the churn rate. And yeah, so here in this piece of code, I've split the data. And as you can see, the X train shape is 4,930. Here you got your 45 columns. Your Y train is also 4,930, your X test, Y test shape. So yeah, here if you see the X train data, this is before normalization. You can see the monthly charges. So these datas were already in binary, so it's fine. It won't be affected by normalization. But here, if you see the monthly charges, here you can see the scale is quite different. So after you normalize this train here by fit transforming, you are yeah, there we go. You get the standardization. You get the standard model, the standardized data, sorry. And the similar thing is done with the X test. So now we get to the interesting part, the model building part. So let me go ahead and explain what this is. So what a dense layer is. So let me explain what a dense layer is. So if we look at this, X1 is connected to this neuron, X2 is connected to this neuron. We can see that every neuron is connected to the input layers. So if every neuron is connected to every single neuron of another layer, so that means if every neuron of input is connected to every neuron of a hidden layer, that's called a dense layer. So this first layer is a dense layer with the input shape of 45. So if you guys had caught on earlier, 45 is the number of columns we have, basically the attributes of the data. So that's why we put 45, and we use the activation of ReLU. So as I mentioned, ReLU is basically the mod x function. So any negative values become 0 and the positive values remain the same. So what I've done here is 45, because, well, 45 columns. So that's basically 45 input features. Then I've added another layer of 60 neurons. So here there are 6, so just 10 times the amount of neurons. That's the first hidden layer. The second dense layer is, sorry, the second dense layer is how many neurons? 32. So that's like 32. And then I've added another dense layer of 16. So that's adding another hidden layer. And that has 16 neurons, same ReLU activation. And the last layer is the output layer. Here the output isn't mentioned as a neuron form, but you can just, since it's one, there's only one neuron because we're predicting yes or no. And we're using the sigmoid. So sigmoid, what it does, I told you, it restricts the neurons output to 0 and 1, which is basically what we need for a classification problem. Either they churn, which is 0, or they don't, which is 1. Okay, so here there's something known as an optimizer. So an optimizer is very, like, to put it in simple terms. Okay, let's say, let's take the. Okay, let's reduce this. Okay, let's take. Okay, so okay, so I'll tell you what epoch is. So, but before we move on to epoch, well, let's talk about the optimizer and what it does basically. So let's say you've started the model. The model has assigned random weights. Like as I said, you get X1 and then you get a random weight associated with it, W1. W1 and W2 here. So this is just a weighted summation of W1, W2. And this also acts like, so this hidden layer acts as the input layer for this particular hidden layer. So again, it has some weights associated with it, and based on those weights, it goes into that into the other hidden layer, and then you get the output. So from going from here to here to here, like till the end, that's what you would refer to as forward propagation. Now, let's say you've got a certain output, but the output is the loss as in how far it is from the actual true value. So let's say you were predicting the cost of a house. Let's say the actual cost was 1.2 crores, but your model predicted it to be 2 crores. So your loss, a simple loss that we can take is 2 crores minus 1.2 crores, which is 8 crores. So our idea is to bring that loss, which is 8 crores, to as low a value as possible. So in order to do that, we do something called back propagation, which is basically feeding the back propagation is basically adjusting the weights in order to minimize the loss. So that's what your optimizer is. So your optimizer basically reduces the loss by retraining the weights, by reassigning the weights. So far, the best optimizer is Adam. There's a research paper on it where they compare with different data, but there may be certain exceptions. So, like I said, deep learning is all about trial and error. So whether you get it or you don't, you have to just keep experimenting until you find something that you are happy with. So yeah, and here the metrics is we're taking accuracy. So the loss here is binary cross entropy. That's another type of loss function. It basically actually yeah, like I said earlier, like let's say that 8 crores you're trying to reduce it, so it basically reduces the error for a classification problem. So you would use binary cross entropy for a classification problem. That is where your output is restricted to 0 and 1. Okay. So here I fit the model. And epochs. So yeah, let me explain what epochs are. So you know what forward propagation is basically from here all the way to here, that's forward. Backward is adjusting the weights to get a better output. So that entire process of going forward and then getting feedback, that's one epoch. So here I've kept 100 epochs. You have to experiment and try to keep you have to find a suitable amount because you want to avoid overfitting. Okay, so here I've trained the model, and here we've made a prediction with model.predict. And since it's a classification problem, we use something known as a confusion matrix. So the name, it sounds quite complex. It does sound confusing, but it's quite simple. You're basically, for a classification problem, one of the metrics is a confusion matrix. So what it does is it considers your actual values and your predicted values. So if your actual values and your predicted values match, then it's a true positive. If your model has predicted that it's true, but it's actually false, that's a false positive. So I can better explain it with this diagram. So here, this is a true true positive where the model has predicted a customer would churn and they actually churned. Here is where the truth is they did churn, but the model predicted that they where they didn't churn, but the model predicted that they churned. And similarly, these are the other ones. And yeah, so how you would so the metrics you would use to measure the performance of a classification model are your accuracy, precision, recall, and F1 score. So accuracy is basically your true positive, how many times the model predicted true and it was actually true, divided by your true positives plus your basically your total the total input. So here the model's accuracy is 75%, which is not quite great. So we can tune the layers, we can design a different architecture. Maybe if I add more neurons, or a different layer, then we may get a better metric. So those are different optimization techniques. Okay, and precision is basically how precise your model is. It's in the name itself. And then you got recall and F1 score. So precision is a positive metric. So the higher your precision, the better. Recall is a negative, also a positive. The better recall, the better it is. And finally, your F1 score, which basically combines both your precision and recall. It's I don't remember the exact formula for it, high, uh, but it boils down to basically the higher the F1 score, the better your model is. So yeah, that's what I had in store for today. I hope you guys enjoyed this session. If you have any questions, do let me know. I will read the comments. Okay, so we've got a question. Does more number of epochs affect accuracy? Yes, the accuracy does. It depends actually, but generally speaking, if your if your epochs are too little, obviously it'll drastically affect the accuracy. But wait, let me just show you. Okay, so we see at the start the accuracy 76, and as the epochs increase, the accuracy also increases. But at one point, your accuracy like stalls basically. So let's see. Sometimes we've gotten better epochs at a earlier stage than a later stage. So it depends. It entirely depends on how your model performs with that particular data. But in a general rule of thumb is yes, uh, the accuracy does depend on the number of epochs. Okay, do you guys have any more questions? Okay, cool. I don't think there are any more questions. So this was uh, demystifying the machine learning. Yeah, yeah, demystifying machine learning. It is quite it is a simple concept, but it does require practice, like repetitive practice, for you to truly understand the concepts. And it's something ever changing. You can never truly 100% be confident with deep learning or any other machine learning algorithms because it's ever changing. And yeah, so that's about it. Okay, thank you guys so much for attending the session. I will